And in this video, we'll see how we can calculate the moment of inertia for a solid object, and more specifically for a solid rod that it is available to rotate through its center of mass or through one of its edges, or for a non-uniform rod that again it is rotating through its edge. As you probably know, the definition for the moment of inertia for a system of masses is summation of mass times r squared for every single mass, where r is the distance from the point of rotation or from the fixed point. Now, if we have a solid object, this law changes into integral of r squared multiplied by dm, where dm is an infinitely small mass of the object, and r is the distance from the point of rotation. So let's start for the first case, which is a uniform solid rod that it is rotating through its center of mass. Now, if we consider that the rod has a length L, all we need to do is try to apply the law of integration r squared times dm. Now, since the rod is a stretched object on the x-axis and r is the distance from the fixed point, it's a little bit better to consider that the r is actually the x-coordinate. So the integral changes to x squared times dm. And this creates a small issue because our integration has the variable of dm, of mass, but the main body of the integral is the x squared, which is distance. So somehow we need to change this dm into something that contains the dx. We can do this by considering the concept of linear mass density. We consider that there is a linear mass density, and we call it with the letter lambda, and basically it means the mass divided by the length of the rod. Now, this also means that if we consider that we have a very small mass that we call dm, this very small mass has a length that we call dx. So, at the same time, the linear mass density is dm over dx. Now, if we take the second part of this equation, we bring that dm is equal mass over length times dx. So we can bring this into our integration, and we have x squared multiplied by m over l dx. And this solves our problem because our integration is for dx, and the main body of the integration contains this dx. So what we need to do now is set the limits of this integration. And if we consider that the center of mass is at the origin, then, and every point dm has a distance that we call x, then the left edge of the rod will be at a distance that it is L over 2 to the left side, so minus L over 2. And the right side of the rod would be at a distance length over 2 to the right, so plus L over 2. So the coordinate x varies from minus L over 2 to plus L over 2. So now we get that the integral is, we can bring the m over L outside the integral. X squared integrated is x to the power of 3 over 3, and all we need to do is set plus L over 2 and minus L over 2 in the place of x. So we have m over L, and we open up a bracket. L over 2 to the power of 3 means L to the power of 3. 2 to the power of 3 is 8, so 3 times 8, minus, we do the same thing with the minus L over 2, so minus L over 2, L to the power of 3 divided by 3 times 8. And from this we bring that we get m over L to the power of 3 over 24 plus L to the power of 3 over 24, which is L to the power of 3 over 12. And if we cancel one L from the top and one L from the denominator, we get mL squared over 12, which is the value for the moment of inertia through its center of mass. Now we can continue to our next case, which is very, very similar. We need to find the moment of inertia for an object that, for the rod, that it is rotated through its left edge. So let's consider again that we have this long rod, and there are two ways to find this moment of inertia through its left end. The first way is by using what we call the parallel axis theorem, or Steiner's theorem, Steiner's law, that states that the moment of inertia for any point is equal to the moment of inertia of the center of mass plus mass times the distance to the power of 2, where d, distance, is the distance between the point where we consider the moment of inertia and the center of mass. Now, if we try to apply this, we get that the moment of inertia is mL squared over 12 plus m. This distance between the center of mass and the left end is half the length of the rod, so it is L over 2. So L over 2 to the power of 2. So this is mL squared over 12 plus mL squared over 4. And in order to add these two fractions, we need common denominators, so times 3 times 3. This brings 3mL squared plus mL squared. It is 4mL squared over 12. And if we simplify, the final result is mL squared over 3. However, another method is to again apply integral calculus. So if we do that, what we get is that the moment of inertia for the left edge is moment of inertia is integration, again, x squared times dm. But now my position where I start from is the left end of the rod, so I consider that this position is 0, and moving to the right, the integration should finish at the length of the rod, so it is from 0 to L. And again we apply the same method. We say that the linear density is mass over the length of the rod, and this is also equal to dm over dx, and this means that the dm is equal m times dx over L. So practically we have the same integration, x squared times m dx over L, but the limits are from 0 to L. So we bring m over L, x to the power of 3 over 3, with limits from 0 to L. This means mL squared, m over L, L to the power of 3 over 3, so mL squared over 3. And we see, by using the two methods, we bring exactly the same result. The last case where we will try to apply for the moment of inertia is the moment of inertia for a non-uniform object, a non-uniform distribution of mass, where somebody might give you a function for the linear mass density. For example, he could tell you that the linear mass density is 2x. Now, what this means? This means that the mass, or more specifically the density of this rod, depends on the position. So if we consider that the left end is at the position x is equal 0, and the right end is at the position x is equal L, because the length of the rod is L, then the mass of this rod varies with its distance from the origin. So, for example, for small values of x, there is small or even zero mass density. So we can consider that it is less dense in particles, in materials, and as the distance increases, it becomes more dense and more dense and more dense. So we have an uneven distribution of mass through the rod. So the rod is much heavier on its right side in this case. Now, this doesn't change too many things in your calculations. Again, if you need to find the moment of inertia, you need to have moment of inertia's integration of r squared dm. And again, because this rod is extended on the x-axis and all the dm's are on the x-axis, it is a little bit better to say x squared times dm. And the only thing that we need to do is say that this given linear mass density is dm over dx. So from this part of the equation, we get that the dm is equal to x times dx. And the integration is happening from the start to finish, x squared times 2x times dx. So this is an integration from 0 to L to x to the power of 3 times dx. The integral of x3 is x to the power of 4 over 4, and we need to substitute 0 and L. This means 2 L to the power of 4 over 4, or L to the power of 4 over 3. Thank you for watching.